In this video, we're going to talk about linear dependence and span. And just a couple of refresher definitions. We're going to first talk about what a set is. A set is just a collection of objects. For us, we're going to be looking at a collection of vectors. And we say that X belongs to, or is a set, is a part of the set. We say X is an element, or it belongs to. If X is in that group of objects, and in this case it would be a vector. If X is not in that set, then we write it with this form, with this funky looking E, means element or belongs to. And then with that line through it means it does not belong to, is not an element. So as an example, we have a set of vectors. These are my three vectors. These could be x1, x2, x3, or u1, u2, u3. It doesn't matter that we have these three vectors. Then we define a subset. So we say that S and T are two sets. S is a subset of T if S is completely contained or is at least equal to. So this means contained or equal to is a smaller group of the original set. We say it's a subset. When every element in the set S is also in the element of T. As an example, I have my set of vectors T, which is this, and then a particular vector I pulled out, which is 2, 1, negative 3, is a subset of T. Again, the 2, 1, negative 3 is this vector. This is a subset of T. And we need that when we start talking, and we just needed to refresh ourselves when we start talking about dependence and independent sets and how to make a smaller set that is independent from a larger set that is dependent. So that's why we needed just to have a moment to talk about subsets. So first we're going to look at the first theorem, which is dependency and linear dependent sets. Suppose that we have some set of vectors S. We say that S is linearly dependent if and only if there is some index, there's some vector within my linear combination of my set. Now this T is just some vector, but not necessarily the last vector or just any vector, bigger than 1 or the last vector, so that I can make a linear combination of the vectors to equal this particular vector. So let's take a look at an example of what this theorem says. Basically, the result of this theorem says that we can whittle down our set of vectors to make it a smaller set of vectors, so we can find a subset that is linearly independent. Now we know by looking at this that our number of entries here is 3. So this is coming from yesterday's video. We know the number of entries is 3, but I have the number of columns I have. N is 1, 2, 3, 4. So I have 5 column vectors. Because N is larger than M, we know that we have dependence. So we know these are linearly dependent. So what we want to do is we want to whittle down the vectors in here that are extraneous. We don't really need them. They're not extraneous, I should say. They're just duplicates because they're linear combinations. So let's go ahead and try to whittle this down to a smaller set. We want to go to a subset. So the first thing we're going to do, of course, is put it into a matrix and row reduce it. When I put this into a matrix and I reduce row echelon this matrix, this is what I get. I get 1, 0, 0, and 0, 1, 0, and 0, 0, 1, and 2, 1, 0, and negative 1, negative 2, and 0. So that's what I get. So our free variables are right here. This is x sub 4 and x sub 5. These are my free variables. And I know that with my linear combinations from my last video, I can make my linear combinations, or my null space, if you will, of B, is going to be the coefficients that represent the x4 and the x5, the free variable coefficients. So I'm going to end up with these two vectors here, where this is my x sub 4, my z sub 4, and my z sub 5. These are my null space. And I know that in my x sub 4, my first position is a negative 2, and then on my z sub 5, z1 and z2, with Z1 and Z2, where this is the X4 coefficient, this is the X5 coefficient. So not abuse the notation here. Anyways, so, and then my my other vectors, I fill this in as a positive 1. Then my second position is going to be a negative 1 and a positive 2. And then my third one is going to be 0 in both of those. And that's because here's my x sub 3, and it's in terms of neither one of those. So neither one of those are x sub 3. And then my x sub 4, my free variable there, and then my last one, x sub 5, which is my free variable there. Now, if I take a look at, I have my first one, which is negative 2. I'm going to call, and then V1, because I already labeled V1. And then the negative 1 V2, and I'm using, what I'm doing is I'm using this first column here. And then plus 0 V3, and then plus 1 V4, and then plus 0 V5 is equal to 0. So now I'm going to use the second vector here. So I have 1 V1 plus 2 V2 plus 0 V3 plus 0 V4, and then plus 1 V5 is equal to 0. Now what I did was I used these as my scalar multipliers with each one of these vectors. And you notice on either one of these, whether I'm using this first set of equations or the second set of linear combinations, not equations, linear combinations, that I have a 0 times a V3. So I'm going to choose that one to be my part of my linear independent set, because no matter how I do it, the coefficient to make these linear combinations work to be 0 is that the coefficient on V3 is already 0. So it's already got the trivial solution part, if you will. So I know I'm going to use that one. Now, if I look at this first equation here, so let's just look at this first linear combination. And if I solve for x sub 4 in this first linear combination, or v sub 4 I should say, so if I solve for v sub 4, what I'm going to get is 2v sub 1 plus v sub 2. So what it looks like is that v sub 4 is a linear combination of v1 and v2. Now if I take this one and set it and solve for v5, v5 is going to be negative v1 minus 2v2. That means v2 is a linear combination of v1 and v2. So the subset that I'm going to choose that will be linear independent, and it has the 3 vectors, is going to be those 3 vectors. So my choice, my subset T, will be the v1, v2, and the v3. Or in other words, my vectors are going to be 2, 1, 1, negative 1, negative 1, 1, and 1, 2, and 3. And these are vectors with commas between them. So that is the subset. T is my subset of my set W, and those will be linearly independent. Let's take a look at this example, or this theorem here. This theorem is the basis of the span. Suppose we have the set of vectors is a set of column vectors defined where W is the span, and let A be a matrix whose columns are the vectors. Let B be the reduced row echelon form of A. Then D, my dependent columns, D1 to D4, are the set of indices for the pivot columns of B. That's no surprise there. Then T is going to be a linear independent set if I use the vectors with those pivot columns. And in particular, that will generate and span my set W. The proof is in your book for your viewing pleasure. So using that theorem, what I'm going to do is, I know just looking at it from my previous theorems and my last section is that the number of entries is 3, the number of columns I have is 4, so we know we have dependence. I go ahead and put this into a matrix and reduce row echelon form, and for this example I'm going to get this 1 0 0 0 1 0 negative 1, so we know we've got a non-pivot there, and then 1 1 0. So my pivots are in column 1 and column 2. So this one and this one are my subset that are linearly independent, and those two will generate these other two vectors. So my t, which is going to be a subset of S, my t will be the vectors 2, negative 1, 2, 3, 0, and 1. Okay, let's take a look at my next example. And once again, I'm going to reduced row echelon form this. I'm going to put it into a matrix. I'm going to reduce row echelon form. And for this one, I end up with this matrix 1 0 0, 0 1 0, 2 1 0. So we know that's not a pivot column. 0 0 1. Oh, I found a pivot column, and then 1 1 0. Okay. My pivot columns happen in 1, 2, and 4. So 1, 2, and 4 are my linearly independent. That is my t. So my t will be the subset of S, and so my t will be the vectors 1, 2, negative 1, 2, negative 3, 1, and 3, 1, 1. So those are the three vectors I'm going to choose to be my spanning set, which is a subset of T of S, that will span, T will span S. Okay. Now for this example, they're asking me to find two different subsets. Right until now, I've chosen one subset. This one I want two different subsets. And so, of course, my first reaction is to go ahead and put it into RREF form. And when I do that, I get this equivalent matrix, and 0 0 1 and 2 negative 1 1. Now we know the easy one is the first subset. The easy one is my pivot columns. So the first choice for R, which is a subset of S, a subset of T in this case, my first choice for R is going to be the vectors 1 negative 1 2, 3 0 1, and 4 2 3. So that's my first choice. Now what I'm going to do is choose a second way. And the way I'm going to choose the second way is I'm going to find my null space. So I'm going to find the null space of A. To find the null space of A, I'm going to be finding, this is my Z1. My free variable is only, by the way, my x sub 4, because that's my free variable here. It's the only one that's a free variable. So, excuse me, my entry in my first position is going to be negative 2, and then 1, and then negative 1, and then 1. So that is my linear combination that I'm going to use. So I know that it's going to be negative 2, I'm going to call this V1, plus V2, so there's V2, minus V3, here's V3, and then plus V4, here's V4, and I'm going to set this thing equal to 0. If I rearrange it, and I can rearrange any of the ones I want, I'm going to rearrange it, say, with, I don't know, I'm going to rearrange it so it's V2. So I'm going to solve for V2. So V2 is going to be a linear combination of 2V1 plus V3 minus V4. So that is a linear combination. So that tells me that V2 can be replaced with a linear combination to get in terms of V4. And so another possible solution is I'm going to take the first vector, my third vector, and my fourth vector. So here's another potential combination. And so I've got this, I'm going to call this S, which is a subset of T. So I'm going to use the first vector, which is 1, -1, and 2. I'm going to use the third vector, which is 4, 2, and 3. And then I'm going to use the fourth vector, which is 3, 0, and 6. Now, could I have solved for one of the other vectors? Sure. I could have solved for one of the other vectors. I could have taken and said, okay, I'm going to, instead of solving for V2, I'm going to solve for V1, or I'm going to solve for V3, or I'm going to solve for V4. I choose it just randomly, but I do know that this will be, if I put this into reduced row echelon form, it will become the identity matrix. I could have chose here, because of my linear combination, I could have chose to replace the first vector. I could have chose to replace the third vector. These three other ones I could have chose to replace being a linear combination. Notice that I did not choose to replace V4 because by default, V4 is already a linear combination because I chose my pivot columns, leaving V4, which is where my free variable lands. So I would not replace V4 with one of these because it's already done in this first choice. Here is a second choice, and again, I could have chose a different one by replacing V1, and I could have said, hey, you know what, let's solve for V1. So here's another choice. So V1, -2 V1, is going to equal V2, -V2, plus V3 minus V4. But the problem here is that I'm going to end up with having to divide everything by a -2. So I will have V1 is going to be equal to a 1/2 V2 plus a -1/2 V3 plus a 1/2 V4. So what I would have had to have done is I would have had to taken all the entries of the V2, the second vector V2, and divided them by 1/2, or in other words, divided by 2, multiplied by 1/2. And the same thing with V3 and V4. So you can choose V1 as a replacement, but because of that coefficient makes it a little cumbersome, you probably don't want to. And that's it for this section.